So this is joint work with, based on some joint works with Jayakumar Radhakrishnan and Atri Rudra. So let's get started. So I don't have to remind you of this. This is the first slide on communication complexity. Anup yesterday talked a great deal about communication complexity and its fantastic merits. So I can quickly skip this slide just to remind you there are two players in the classical model of Yao. There are two players, Alice and Bob, and they are given inputs x and y. I'll do a very quick recap of this. And they want to compute some function f which jointly depends on x and y. Alice only knows x, Bob only knows y, and therefore by themselves they cannot compute, although they have unbounded computational power. So in this talk, just in the spirit of communication complexity, all computing agents will have unbounded computational power. And therefore, they decide upon a protocol beforehand, and using that protocol, they communicate with each other, perhaps taking turns, where what they communicate at each point depends on what the player has in his or her hand and what has been the communication history thus far, right? And so at the end of the rth round, perhaps in this case, Bob sends the final answer and Alice gives out the answer. So the aim is to minimize the communication cost and the complexity of any function trivially. By now, I'm sure you know this, is at most n plus 1. And the whole point is to find out for what functions can we reduce this cost from the trivial n plus 1. Okay? So, and as Anup was saying yesterday, there are many, many applications for communication complexity. I think when Yao formulated this model in 1979, I think it was called, I don't remember the exact title of the paper, but it was called something to do with VLSI and distributed computing. And I think it's a fair statement to say that he didn't realize what a fantastic model he had introduced, and now it has many, many applications in data structures, circuit complexity, pseudo-randomness, combinatorial optimization, property testing, and many things in theoretical computer science. So much so that it has been called the Swiss army knife of computer scientists. And many situations where we don't know how to solve the problem, as we saw yesterday, communication complexity is the way to go in many situations. So what we are going to talk today is slightly not about applications, so to say, but what started as an intellectual curiosity, which is, what happens if I sort of try to extend this two-party classical communication to the multi-party case, okay? And mostly what Anup was talking yesterday when he talked about multi-party is this sort of famous or infamous number on the forehead model. But I'm not going to talk about the number on the forehead model. What I'm going to talk about is often called the number in the hand model. In some sense, the number in the hand model is what you would think to be a natural generalization of the two-party model. So in this particular model, there are k nodes, and the version that I will look at is not the broadcast version. So in this network, there is a node at every vertex of the graph, which has got unbounded computational power as before. And this graph specifies the way nodes can communicate with each other. Right, so the communication is point-to-point. You can only communicate with your neighbors, as is the case in distributed computing. And since I will be interested in mainly improving lower bounds, I will sort of make this absurd assumption, which is that there's public randomness. Although it's distributed, players have common access to public randomness. This only makes the model stronger, so any lower bounds that you prove assuming public randomness, of course, implies lower bounds for more realistic models. Okay. So as I said, the one key difference here will be that the communication is point-to-point rather than being a broadcast communication. And what we would be interested, there are many interesting parameters. I mean, in some distributed computing, what we saw was some talk on distributed computing. One key thing that they look at is the number of rounds, which is a measure of the time taken to to compute something. However, in this talk, what I would be solely interested is in the total communication. And the total communication would be the sum of the total number of bits that get communicated across all edges of the network. Okay? And the idea is that, in two-party communication, it's a pretty interesting and vibrant theory now, where we have many interesting results for relating the combinatorial structure of a Boolean function with its communication complexity. Now we would like to do the same here on this, where one would hope that there's some interesting interplay between the graph structure of the communication network and the combinatorial structure of the function, and the communication complexity should depend on both. Okay, so the topology of the network and the combinatorial structure of the Boolean function should have a role. And this seems little explored, so I should make a note here, because a remark, which is that, of course, distributed computing people have looked at this kind of things, but there's a key difference here. One key difference is in this model, I will assume the players beforehand know the network. Whereas in distributed computing, what we saw was the network was unknown. So when they prove lower bounds in distributed computing, they would say that there exists a graph for which you need to communicate so and so, right? The graph itself is the input. The players have to sort of discover the graph as they go. Whereas here, we will assume that the network is fully known to the players, and so they would design a protocol based on their knowledge of the network. The network is not going to change as communication takes place. Okay? So when we will prove lower bounds, it will be lower bounds that work for every graph. Okay? So why care about this? Well, as I said, it's a setup which is sort of very closely related to distributed computing. It's a very natural setup. It seems to naturally generalize to two-party communication complexity to multiparty. And in the literature, there has been connections made with this model to distributed functional monitoring. Well, of course, our brain is some sort of a network where perhaps a network is fixed, and you would want to understand how communication happens, what is the total number of bits communicated to compute some joint function. So again, let me just make sure that the model has sort of sunk in. So I have a graph which is connected, so otherwise it doesn't make sense. And there are k players which will sit on nodes. So these k players, this is not working, sorry. Maybe. No. So anyway, so there is some subset, big capital K, of the total number of vertices, total set of vertices V, which are special in the sense that these nodes in this capital K will get some inputs. They are called terminals. And then there are other nodes in the graph that are there to facilitate computation, but they don't have to begin with any input. But they might aid the computation in ways like assimilating information from various other parties and computing something meaningful. So they have computational power as any other party, but they don't have inputs to begin with. Okay, so there will be some special set of nodes which have input. So in this particular case, the nodes that are shown in red are the ones that have inputs. The nodes that are shown in blue, they participate, but they don't have inputs. Okay? And the players who have input, each such player has a private n-bit string. They want to compute some function f, Boolean function, which is again known to all the players. So it's just a Boolean function that depends on nk bits. Okay? And as I said, I want to minimize the total number of bits communicated in the worst case in the spirit of communication complexity. Okay? Let us say at this point I just care about some node knowing the answer. Okay? But you could just say that the one bit after one node knows the answer, that one bit could be propagated back to all other nodes, but for simplicity, we will note some node knows the answer. Okay, and you only communicate over the edges of this graph. So as I said, all the other players also participate, players who do not have inputs. So again, for simplicity, I will assume that it is some sort of a synchronous model, some reasonable synchronous model. In particular, the following thing would be key. Okay, so you cannot use sort of silence to communicate something. Meaning, if somebody was expecting something from you, and a player, so there are two players, player A and B, they are connected by an edge. B, so far from the state of his communication history, believes that there is a possibility that A might communicate, and let's say A didn't communicate on the tick of that clock, that would count for 1 bit. Okay? So if somebody is expecting you to communicate in some, if in some other run of the protocol consistent with what you have seen so far, B thinks that there could be some possible communication from A, then if A doesn't want to communicate, she has to still transmit 1 bit. Okay? So this is going to be the model. Okay, and now let us consider two functions. So just to illustrate this thing, the two functions that I will look at are very simple functions. The first one I will call is element-distinctness. So in this particular function, you output 1 if all the elements, the k element, the k n-bit strings that you get, they're all distinct. None of them is the same with each other. Okay? Then you output 1, otherwise you output. So if any pair of them is equal, you output 0. Right? And the other function is the equality function, in which case you output 1 precisely when all the k strings are equal to each other. Okay? This seems fairly similar, but if you just think about it, they have very different topological behavior. Okay? I will try to convince you. It's actually quite simple. But before I do that, what happens if k is 2? In the classical Yao's model, these two functions essentially coincide. Okay? Because you want to understand, if you're given just 2 strings, the knot of the element distinctness is the equality function. Right? And just to remind you of how do you do that in the two-party model, well, first of all, if you only have deterministic communication, then equality is a very hard function in the two-party model. One can show that you need to communicate, essentially one player has to communicate, Alice has to say communicate all her bits to Bob, and then Bob gives the answer. So you require n plus 1 bits of communication, and you can't do anything better. However, if you have randomness given to you, then and for the purpose of this talk, as I said, I'm going to always assume public randomness. Okay? So then there is this simple way of sending your hash, right? You toss random coins. Alice sends the hash of her string using this set of random coins. Let's say the inner product of x and r modulo 2, which is 1 bit. And then Bob checks if his string also hashes to the same. And if not, he detects a difference. Otherwise, he says yes. Now it's simple and well known that this with probability exactly half will give you the right answer. If the 2 strings are the same, it's one-sided. So if the 2 strings are the same, you always give the right answer. If the 2 strings are different, you catch with probability half. Okay, and you can sort of repeat this for a few number of times and bring down the difference. As I said, so therefore element distinctness or equality in the two-party case is the same. So we know for deterministic communication for k equals 2, you require n plus 1. You can't do anything better. For randomized, it's order 1, right? Both the functions, because they coincide. Now let's go back to the model for a general k, and let's choose a specific graph, which is this sort of path or line. Okay? And there are k players. So for simplicity, I have assumed now each player is a terminal. Okay? And in this case, if you think about it deterministically, it seems, well, what can the players do? The first player, so we're looking at the equality function now. Okay? So the first player, x1, has to send her n bits to x2. Well, then x2 checks if x1 is the same with her input, and then if it is, she transmits her n bits, and so on, right? And so eventually maybe some player discovers, well, the strings are not the same, and then they output the answer. So in this case, it seems the deterministic cost of this function is, well, on the path is k minus 1 times n, right? And it's not very hard to prove that you cannot do anything better. Okay? I mean, it takes an argument. Now let's come back on the same graph and look at the element distinctness function. Well, I mean, okay, let's say plus 1. I'm not worrying about the plus 1. And as I said, I will just assume that if some player knows the answer, the protocol terminates there for simplicity. Okay, otherwise I might have to even do a plus k to propagate things to every player, right? Okay, so but let's not worry about that. So now if I look at element distinctness on the same graph, well, now what would you do? Well, the player, of course, it seems like the first player has to send n bits, her entire string, to the second player, because they have to be sure that, you have to send n bits because they have to be sure that the two n bit strings are distinct. Sorry? Well, yeah, sort of, not quite, I don't know why you're saying k choose 2, but yeah. So yeah, but asymptotically it is going to be the same. So now the player 2 will have to, well, now player 2 cannot suppress the n bits that came from player 1, right? Player 2 has to propagate that further. So every time as you propagate down this information, the number of bits is increasing, because in order for player 3 to be sure that her string is different from both player 1's and player 2 strings, she needs to receive both of them, right? And so now if you do this, it seems like what you should do is you should identify a sort of a convenient node, like the middle node in this case, where from both sides players are sort of sending their bits, and if you work out the math, well, then it seems like it's order k square times n, right? So of course, these two behave quite differently. It seems so. I mean, I haven't proven anything, but if you naively think about it, it seems, well, you can't do anything better. Again, this can be shown. The deterministic, in fact, for the deterministic case, it was known before that on the path you would need sort of omega k square n for element distinctness, and for equality you need k minus 1 times n. So the purpose of this was just to sort of convince you that now when you have multiple parties, players, this element distinctness and equality functions, they start behaving quite differently. The amount you need to communicate should depend on the graph, right? So that's what I meant by different topological behavior. And again, if you, I'll just run through it fast. Now, if you want to run a randomized protocol, you could be inspired by the two-party version of it. In the case of equality, what we did was to send the hashes. So you do the same thing. Just basically instead of sending n bits, every time n bits were sent in this protocol, in the deterministic protocol, you send your hash. You have infinite public randomness at your disposal, so you can do that. And the randomized cost of the equality function would be order k. And for element distinctness, well, there's this extra log k I have inserted. It's just for the union bound. Just ignore it. Okay, so it's about order k square. Okay, so again, randomized, it looks that they behave differently. Okay, but now how do you prove this? This is, can one show that this is what is the optimal behavior? Okay, so this is how, when we were working with this, with Jayakumar and Atri, this is the problem that got us started. So let me just mention some previous work. So as I said, Yao's model is a very special case of this model because it's just an edge. The graph is just an edge. Okay? And actually, we were not aware of this way back in 1984. Tiwari had considered exactly this model, but he considered, there are two differences. He considered special graphs, so graphs like the paths or a grid, okay? And he also looked only at deterministic communication complexity. So when I said, for example, for deterministic communication, we can show this. We can show that element distinctness and equality behave differently on the path. This is due to Tiwari. Very recently, there's been some very interesting work involving the star. Okay, this is often called the coordinator model. So the node in blue in the star is called the coordinator. This person does not have any input, but since everybody has to go through him, that is why he's called the coordinator. And all the leaves are terminals, shown in red. They have input. And Phillips, Verbin, and Zhang, and Woodruff and Zhang, they proved sort of quite interesting results for the star graph, both for deterministic and randomized communication complexity. And the complexity of set-disjointness on the star graph was not known, and later Braverman et al. They were able to show that you need to basically, the naive protocol is the best protocol for computing set-disjointness. You will require about k times n bits of communication even in the randomized case. And the proof of Braverman et al., if you're interested, actually uses information theoretic tools. So they have to generalize the two-party set-disjointness lower bound, build some new information theoretic tools to prove that. Okay, sorry. So as I said, the number on the forehead model is something that I'm not going to consider. And in the number on the forehead model, communication happens in broadcast mode, whereas here it's in message passing. So hereafter, I will just not talk about the number on forehead. So element distinctness. So what can you do? So if you think about a general graph, yes.
So there's some connection between algorithms and protocols for setting on some graph. Do you know about this?
No. Since you came in late, I just want to remind you. I mean, because I. Well, so I sort of stressed one point. I just want to re-stress it, which is that. So in this model, the protocol designer has the full knowledge of the graph, unlike the distributed computing model. Yeah. So I don't know. Yeah. The only paper I sort of.
Maybe let me ask you a general question. Is there a connection between algorithms that don't build graphs and these models?
Well, there are connections between algorithms. I mean, there are very obvious connections. You are right in that sense. You will see that you're perhaps predicting what is going to come. Like the techniques that we will use eventually to deal with general graphs are, of course, going to use tools that have been developed for designing graph algorithms or approximation algorithms and so on. So in that sense, there is definitely a connection. But I'm not aware of, other than Tiwari's work, I'm not aware of any other. Okay, so let's look at element distinctness. So I want we want to find out if the terminals, the strings that each of the terminals have are distinct. And so as I said, re-stressing it. So in a general graph, what would you do? When it is not a path, you try to identify. I mean, naively, you try to identify a node which is here shown in green, which is sort of at the center. Right? By the center, what I mean is, if you look at the sum of the distances of that node to all the terminals, this sum gets minimized, right? And then everybody would send in their hash to this node, right? And the node would just give out the answer. Right? This is what the naive thing seems to suggest. Okay, and it turns out that this is the best algorithm for general graphs. Okay, so here sigma g is what I'm calling this sort of. So let me just define this. For a graph, g is okay. So, right. So you're trying to locate a node such that the sum of the distances of the terminals from that node is minimized, and this node may not be a terminal. This node may be a node in the graph, right? So this is what naively you would do, and it turns out that what we were able to show is that this is the cost of the optimal randomized algorithm for every graph up to log k factors. So here in this talk, I will not worry too much about the log k factors because we'll lose the log k factors. Okay, it's actually an interesting problem if you can sort of recover the log k factor. Okay, you will see where the log k factor comes in. It looks like an artifact of our argument. But anyway, for now, let's ignore the log k factor. But this is therefore, so this is where I was saying that this is the difference between, again, sort of re-emphasizing the difference between what you typically see in distributed computing literature is that this result holds for all graphs, right? Not for a specific graph, but for every graph, this is the optimal algorithm. Okay. So in particular, for the line now, for the path, this parameter is easy to calculate. It's going to be k square. For a grid, if you think about it, it will be the central node, and the sum of these distances would be k to the 3/2. So for different graphs, you would have these parameters differently. Okay? So now I want to show you the argument. The argument is actually quite simple if you know what to do, and building on others' work. Okay? So let me try to illustrate this first by looking at the path, right? So we were aiming to prove an omega k square bound for the element distinctness functions. So what would you do? Well, let's look at a cut, right? So we're going to look at a sequence of cuts, right? And I want to argue that when you look at this cut, basically the problem reduces to a two-party problem, right? On one side of the cut, I can place Alice. On the other side of the cut, I can place Bob. And then I want to say that if the global protocol was computing element distinctness, then that induces a two-party protocol across this cut. And since in the two-party protocol I know what lower bounds I want to prove, I want to say across the cut so many bits have to flow. And then I want to do this for, I want to place a cut, several cuts, and then sum up the number of bits that get communicated across this cut, right? So this is what I said. So I place Alice and Bob, and imagine, Alice somehow has inputs which are all distinct. So the global inputs that I'm giving they happen to be all distinct. Of course, the protocol doesn't know this. The protocol has to be correct on all inputs. Okay? So Alice has all distinct inputs. Bob has all distinct inputs. And now if the original protocol was solving element distinctness, then essentially on this cut, if you think about it, Alice and Bob are solving a set-disjointness problem, right? You're getting some elements out of this huge universe. The universe is now not of size n, but of size 2 to the n, and Alice has got some elements, and Bob has got some elements, and you want to see if there's a common element there, right? It seems very simple, right? So the question that the protocol must be solving across this cut is the set with Alice disjoint from that with Bob, right? The size of the sets, the size of the sets are known. But you can still show using any of your favorite set disjointness argument that this will require, so the minimum of the number, so Alice in this particular cut which have there are I nodes on Alice's side. So Alice has I elements, Bob has the rest k minus I. So you can show that the minimum of this I between I and k minus I, so many bits have to be communicated in a randomized protocol. Okay? And so now you would want to say, well, the total cost is going to be the summation of the costs across all cuts, and look, across a cut, I'm exactly counting an edge only once, right? Because these cuts are disjoint. The cut edges are disjoint. So I can sort of sum up this bits communicated, and I can, that should be honest to God lower bound, right? So are we done? Do you think this is okay? Right, so why? There's a problem of summing up.
Just if you count all the bits, all the lines, they are the sum.
It's just the next.
No, but
Right. So
because a lot of information was already passed when you compare on one cut, and so when you are comparing to another cut, still already,
When we count something, we count only.
well, no, but anyway, what I'm saying is that across this cut, no matter what you do,
yes.
so I could sum it up, right?
Yeah.
Well, no, there's a problem. The problem is, it's not much of a problem, but there's one thing one has to take care of, which is that, well, these are, if you think about these as worst case costs, right? You cannot quite sum up in the sense that I'm looking at individual two-party problems across each cut, right? And the sort of the worst case there may not be a globally consistent input, which basically is the worst case for all the induced k two-party problems. Well, it's not, okay, so I don't know how to make that argument. So for example, actually Tiwari had to struggle. So it turns out that if we consider the randomized model in any case, this is not a problem, right? Because I could look at the expected cost. If you prove a randomized lower bound, it's as good as proving an expected lower bound, okay? So, by linearity of expectation, I can sum up the expected cost on these edges, and that's still all right, okay?
The common distribution.
That's right. So this is the important thing. Now, therefore, if I want to do that, what I must do in general for problems is to come up with a global distribution on the inputs such that the induced distribution on the cuts are indeed hard distribution for the two-party problem that I want to invoke, right? And then I can do this. So, however, just as an interesting remark, we can talk offline. This thing you cannot. It doesn't seem that you could use such a trick when you're dealing with deterministic protocols. So, strangely, proving deterministic lower bounds here seem more difficult. Okay. So, as I said, that was the problem. So randomization helps, and just to go through it quickly. So, now I want to choose this hard distribution mu. And this hard distribution for this particular problem happens to be, well, I'm going to uniformly pick k distinct numbers or strings, okay? So every player is getting a distinct string. They are all distinct all the time. But again, I'm insisting on the fact that the protocol has to be correct on all inputs, right? This is a bit like this information theoretic lower bound that you prove for set-disjointness, where you home in on a distribution on which, of course, if the protocol was to just work for that distribution, it would be easy, but you are trying to analyze the expected behavior of a protocol which is correct for all inputs on an adversarially chosen distribution, right? This is exactly the same thing that we're doing here.
If it's correct probability 1, what else could we require? So if there is a notion of do you accept some error probability for randomizing?
Yes. So for every input over the internal random coin tosses of the protocol has to give the right answer with, let's say, probability 3/4.
So what is now random? Input distribution or internal coins or both?
I'm now looking at both. Okay, so the protocol is randomized. Okay, and the protocol has been prescribed. It has the following prescription that for this prescription is true for all inputs. So for every input over the internal random coin tosses of the protocol has to output the right answer with probability, let's say 3/4 for every input. However, if you give me such a protocol, now I'm going to look at its expected communication behavior over this input distribution. Okay? Right, so now I can now I can look at this cut, and now on this cut you get a protocol which is, if your original global protocol was a correct protocol for element distinctness on every input, then you get a protocol which is correct for set disjointness on every input. Okay, this is not hard to show. I mean, it's quite simple. And now as I said, now the induced distribution across cuts is that, the sets are disjoint, right? And one can show that the expected cost using, as I said, essentially any of the theorems for two-party set disjointness, you can show that for this particular distribution, the expected cost of a correct protocol has to be still a minimum of I and k minus I. Okay, and now you can sum it up. So this is just formally saying what I just stated, and you get k square. Okay.
Can you improve that minimum of I, k minus I? Shouldn't it be like I log k?
Well, no, because the Hastad-Wigderson protocol, for example, yeah. So it's tight because there can be. No, but you can tweak it to make it minimum. I think so. I'm not completely sure, but I think maybe you can improve. Okay, so let's now move on to a different graph, the grid graph.
Because I would say the log k factor is fine. That would add log k.
That would add a log k, and I don't know of a way to shave off the log k. If you think about the right protocol, if you think about the naive protocol which has to beat the union bound, it does seem to have a log k.
Oh, so you think that answer is actually the log k?
No, on the line it answers, but for a general graph I will come to it. There are different reasons for losing log k, which okay, for the line that would answer. Yeah, so now let's move on to the grid. So on the grid, I mean, let's say we have a root k by root k grid. Now again, I mean, what would you do? It's a very simple thing to try, right? Armed with this observation, you would basically say, well, let me still go for the same distribution, which is hard, which is basically, I'm going to choose k distinct things. And now the cuts, the graph is suggests the cuts, right? I mean, you basically take vertical cuts and horizontal cuts, right? And then you sum them up. Again, the edges are all distinct, so you can sum them, right? You place Alice and Bob on each side. So sorry, I have some weird thing happening here. So read this as root k, okay? So yeah. And now you want to do the same thing. Is A disjoint from B? And again, the expected cost, this is simple. The expected cost is, just like the previous argument, will be minimum of this I times root k and root k minus I times root k. And you sum it up, you get what you want to get, right? So you can do this for any dimension grids, right? I mean, just a family of cuts for each possible dimension. Okay, how much time do I have? 10 minutes, okay. Okay. Well, so why did I say up to grids? I mean, how many graphs am I going to show you one after the other? It turns out that, grids are almost as good as general graphs. Okay, and this is the non-trivial result. I mean, it's not our result, it's a result that we sort of invoke from the theory of metric embeddings, which is basically if I'm given an arbitrary graph, right, completely arbitrary, it's the remarkable result from metric embeddings, which shows that I can place these vertices on a high dimensional grid, okay, right, such that the following properties are true. So what am I doing? I'm mapping every vertex in the graph to some point in the grid, okay, with the following properties. What are these properties? Well, let's say this edge uv, so u and v is connected by an edge in your original graph. Then the mapped points u prime, v prime on the grid satisfy, well, you don't want the distance because the distance was sort of 1 in the graph metric. And now, when you have mapped it onto the grid, you don't want the distance to become too distorted, too large, right? And they can ensure that. So you want that the distance between what were neighbors does not get suddenly too high. So it's about log k, where k is the number of terminals of the graph, okay? And this grid turns out to be pretty high dimensional. It's not a two-dimensional grid. It will also be a grid of dimension about log of k. Okay? Right. So because I can choose a sort. Okay. For simplicity, assume now here that every vertex is a terminal. Okay. It doesn't matter because I can choose a subset of terminals and induce a graph metric on that. But yeah, for simplicity, let's assume that every node is a terminal.
And the edges becomes disjoint path.
What do you mean become? No, the path is this basically this. It's a grid. The graph is a grid. I'm embedding on the grid.
Yeah, but previous edges of the graph should be now mapped to path on this grid disjoint.
Yeah, so if you have to go to from u prime to v prime, of course you will require to traverse more than one edge. Is that what you're saying?
Yeah, and this should be disjoint.
No, I'm not saying they will be disjoint. No, I'm.
But then when we will put everything.
Yeah, so you're a little ahead. So let me. Yeah, so you.
L1, not how much you.
Yeah, the distance is L1. Yeah. But I can sort of think of it as, you can almost think of it as an integer grid, and just walk it. For our purposes, it doesn't matter. Okay, so yeah, just to answer your concern, we will see that. So now let's look at the other thing. Of course, this is easy to place. All I have said so far is that the pairwise distances, what were pairwise edges do not become suddenly too far apart. Well, you also want the other thing. It's not a contractive embedding. So take any pair wx. Now these may not be neighbors in the original graph. On the grid, the distance, which is the L1 distance, is at least the distance in the original graph. Okay, so you have this sort of two opposing things to be satisfied, right? What you want is the edges should not go too far apart, and what you want is the things should not come too close either, right? This 2 ratio gives you the distortion of the embedding. Okay, and this turns out that you can do this. Okay, so now, so notice that if the distances are so the number of cuts that I'm going to take on the grid, the horizontal cuts and the vertical cuts, the sum total of these cuts is exactly the L1 distance between these vertices, right? W prime and V prime. Okay. Now, how do we prove? So with these things, it doesn't become. It is no longer too very hard to prove this bound. So let's choose this hard distribution, okay, as before. And now we have mapped. We had an arbitrary graph, but all we are doing is playing on the grid after this mapping, okay. So we have, as before, we have Alice and Bob, and as I said, across a cut, you need to, in expectation, you need to communicate that. And let's just, I can show you the proof in its entirety because it's sort of simple and nice. So, let's just rewrite it in this way that I have written, right? So you just take the product. And why am I doing that? Well, if I write it as a product, it's very nice. So it just shows that this is basically the number of pairs that is cut by this, the number of pairs of vertices that are sort of separated by this cut, right? On one side of the cut you have I, the other side of the cut you have k minus I, and you're just looking at the number of possible edges that could have flown through. So this is where the connection with algorithms comes in. These things have been looked at in the algorithms community as well. So number of pairs cut by this cut divided by k. So that's the expected cost. And you can sort of rewrite it. So just 3 more or 4 more lines of simple algebra. So you can rewrite it in the following way. Well, you're basically summing up now over all cuts. What you're summing up is the number of pairs that are cut by each cut, which is the same as, which is the same as saying that how many times, just count it in a different way, how many cuts separate a pair, okay, and then sum over all pairs. It's just a simple way of reformulating the counting, okay. And here's the nice thing. Well, the number of cuts that separate a pair is exactly the L1 distance of this pair, right? Because that was the property. We're using horizontal and vertical cuts. And now we are going to use the nice property of our embedding, which is that every pair is, so the distance, the L1 distance is at least the distance of in the original graph. Okay, so I can rewrite it in this way. Okay. And believe me, this is the same. Now here's the interesting thing to notice is, well, what is this quantity? Well, this quantity is if I had picked this C to be W, right? I mean, the quantity which I've shown in blue brackets. If I sort of thought that, rather than picking the median node, if I picked this to be my purported median node, this would be its contribution, right? The sum of the distances, right? So that quantity is certainly at least as large as it is for the minimal C. Okay? So that quantity is at least as large as sigma g, and you are doing it k times, so you get k times sigma g, the k cancels out and you get sigma g by 2. Okay? Okay, so now we are not done, as you said. Well, but what happened? I mean, various edges I overcounted, as Sasha was pointing out. I mean, the edges are no longer, I mean, the edges were sort of disjoint on the grid, but the edges are not, I mean, the edges that were in the original graph being cut by these cuts, an edge is not being, an edge might occur in very many cuts, right? So when I'm summing this up, I'm overcounting there, right? I mean, the original graph is not on the grid. Okay, so here I need to use the other property of my metric embedding, which is that I haven't used that. I've only used the fact that whatever was pairwise far remained sort of far. Okay? Now, for every edge, what do I know, which is the first property that I said? Well, every edge, which was uv, the distance between u prime and v prime, the mapped pair, is not too large. It's at most log k. That was the first property of my embedding. And therefore, when I look at these cuts that I have done, a particular edge can appear in at most log k cuts. Because the number of cuts that I do between separating u prime and v prime is exactly its L1 distance, right? And they are at most log k apart. So, if you think about it, so every cut that I'm doing here induces a cut in my original graph, and in my original graph, a particular edge is therefore not appearing in more than log k cuts. Okay? And therefore, if I sort of the overcounting that I'm doing, I can I can compensate for that by dividing by a 1 over log k factor.
It looks like we have a bound degree on one side, how many edges are in a cut, and using something for the other side, how many cuts go through an edge.
Yeah. Well, I'm just saying that, well, all I'm saying is that, an edge, what was an edge became at most log k apart. And so in the family of cuts that I'm defining, so every cut that I define here induces a cut in my original graph.
Yeah.
So in the, yeah. So I don't know if you were saying the same, but yeah. Okay, yeah.
It seems like what you want here is a family of cuts where every edge gets cut the same number of times. And if the factor is off by log k, which is what you're having here,
Yeah.
then you get log k.
Yeah.
Is that equivalent to metric embedding?
The way of this, so it's true. For example, if you look at an expander graph and try to do its embedding, then this log k is tight. I mean, there's no way you can avoid this.
If you do the embed, but
Yeah.
what about what I said? Maybe there's a family of cuts that cuts every edge the same.
And keep still the distance apart.
I don't care about the distance. I just want a family of cuts that cuts every edge the same number of times.
No, but you also want the other property that whatever, I mean, the number of times you want to separate a pair has to be commensurate with the distance in the original graph.
That's what I'm not sure that you need. Where did you use that?
Well, I use that to get my sigma g. There were two things I used, right? I mean, I need these two properties as well.
Well, you use it in the sense you only use the stretch of each edge, not how many times that edge is cut.
That's one thing. And then I used also the fact that a pair that was d apart is still at least d apart. Okay, sorry, that was, well, maybe we can take it offline. Yes, sorry about that. Yeah. No, because, I mean, okay, just to clarify that point, I mean, if you just think about the line, right? On the line, what's going on is, if you want to get this k square bound, yeah, it's important that, think, yeah. So you can at least sense that that thing is needed, and it was indeed used. Okay, so I have run out of time, and how much time do I have? Okay, so I just want to say that, okay, just another 2 minutes. This shows hardness for functions like element distinctness, and here sigma g is the right topological parameter, right? Not all functions, and that was the purpose, not all functions will have the same topological parameter. For example, there are functions where the communication cost is essentially the same as the minimum Steiner tree cost. Okay? For example, if you look at, I'm sorry, I'm really out of time. For example, the set-disjointness function, it turns out, it requires an argument, and it's you can show that for solving the set-disjointness problem, the right parameter is the Steiner tree, and let me just say why you should expect that. What's the trivial algorithm achieving that is, you sort of connect it up by connect the terminals by a Steiner tree, and then each terminal, so let it be a rooted Steiner tree, and from the bottom up you're going towards the root. So every terminal on this path essentially tries to see if it finds an intersection or not. Okay, and it just propagates upwards the intersection of the intersecting columns. Okay, so so basically it propagates n-bit strings, because it looks at, so suppose x1 and x2 came together at this particular point, so x1 sent an n-bit string, x2 sent its n-bit string, and then you look at the intersection of those n-bit strings, two n-bit strings, and you find out another n-bit string.
You want a set-intersection problem, the
So,
intersection is empty, is that what you are checking?
yeah, I'm just saying exactly. I mean, I'm doing sort of bitwise AND of things, and I'm propagating it up. So each element does a bit, and you only propagate up the result, right? So you're propagating n bits up the tree, and so you see that it's n times the Steiner tree cost. Okay. Again, this turns out to be optimal. It requires different techniques to prove that, and we were able to show that. Again, up to a log k factor. So in all these bounds, so I'm really out of bound. So this requires some linear programming. Sorry. Okay, so yeah, finally. And we show a bunch of other problems, like a distributed XOR lemma, function composition, and so on. But anyway, so I think it's a very nice area, very little explored, this interplay of sort of graph theory and communication complexity. And one, I mean, here's a bunch of problems. So I defined what is a median type function, right? Element distinctness is a median type function because the median is the right topological parameter. G, so suppose I take another function which is like Steiner tree type, so Set-Disjointness is a Steiner tree type function. And if you compose F composed with G, so composition of functions is a very, very canonical thing in computational complexity. Does the naive way of doing things, does it still remain the optimal? This seems like an interesting conjecture. We don't know how to prove that. Well, the other thing that I was telling was how do I get rid of the log factor? Okay, this seems like an artifact of our trying to embed things. Okay, embedding is the only way that we know how to deal with it, but maybe there is, and for embeddings, as I said, there are classes of graphs like expanders for which you cannot avoid this log factor, but for the communication problem, it's not clear whether you need the log factor. Another thing is like, prove better deterministic lower bounds. For example, look at the element distinctness function. Now, as I showed you, what you should expect is the topology, the sigma g times n to be the cost, right? And for general graphs, I don't know how to prove that. Okay? And more speculatively, just to develop a general theory of communication complexity in this model. Okay? So, sorry, I really went over time. Thanks.